Okay, we should be live now. So, yes, live on YouTube. Yeah, great.
Yep, I see the little streaming icon top
Yeah,
left.
yeah, right, yeah. Okay, good. So maybe we can still wait a couple of minutes and people are still joining a bit and then we can start or whatever you feel like.
Yeah. Let's see. Does it look like it's stabilizing? Yeah, some people are joining. Could wait a
Yeah,
minute.
and I guess people are, someone is also watching directly on YouTube on the live stream.
Right. Yeah.
Yeah,
Of course, we don't know when people join that.
yeah.
I
So
saw.
Matthew, we will keep an eye on the chat if there are questions and if it's something. So don't worry about looking at that, I think.
Great, thank you. And do please feel free to interrupt with questions rather than saving them till the end.
Okay, good. Thanks.
The number seems reasonably stable, so I don't
Yeah.
know. What do you think, Louisa?
Yeah, I think it's fine.
Yeah.
No, I think we can start and then in any case, people can join.
Yeah.
Yeah.
Okay, great. So welcome everyone to the One World Probability Seminar. Today we're very happy to have two talks, and the first one will be by Matt Kahle. Am I saying this right?
Yes.
Yes, by Matt Kahle on an introduction to determinantal random hypertrees. Take it away, Matt.
Okay, thanks very much to the organizers for putting this together and for the opportunity to speak. And um, I'm especially grateful to get to speak in an online seminar this morning and not have to travel, and also for the opportunity to be part of a coordinated double header of talks, which I don't think I've ever done before, and this seemed like a good opportunity to do it. My former PhD student Andrew Newman and I co-authored a paper about determinantal random hypertrees about 5 years ago. And since then, Mészáros has written several lovely papers about them, so about the same model. So I'm happy today to introduce the model and to tell you about a few of Andrew and my results. And I'm happy also for the opportunity to hear whatever András has to say, since I've never gotten to hear him speak before. Okay, so let's get started. This is Andrew, my former PhD student. He's been at Carnegie Mellon for the last few years, and he's starting a tenure track position at Indiana State University starting this fall. I'm excited to report. Okay, so this is notation we may use sometimes in the talk, the brackets n for the numbers from 1 to n. So I'll start by reminding you that there's a well-known theorem in combinatorics called Kahle's theorem that counts the number of spanning trees on a complete graph on n vertices. So the number of trees on vertex set n is exactly equal to n to the n minus 2, a very beautiful formula celebrated in combinatorics. You can find many proofs of this fact. For example, in Agner and Ziegler's book, Proofs from the Book, there's 4 or 5 proofs, that are all quite short and lovely, and some of them generalized in various ways. One way to do this, not the prettiest proof of the theorem, but one way would be with the matrix tree theorem. If you can find all the eigenvalues of the complete graph, which isn't hard to do, then you can essentially multiply them and take the determinant or take the determinant of a certain matrix and come up with this number. So just to illustrate the theorem, give an example, there's 16 trees on 4 vertices, and here they are. I'm not labeling the 4 corners of the square, 1, 2, 3, 4, but you could label them that way. And notice that, many of these trees are isomorphic to each other. In fact, there's only 2 different isomorphism types, but we're not counting isomorphism types. We're counting labeled trees. So then there's 4 squared or 16 trees on the vertices from 1 to 4. If we went up to 5 vertices, it would be 5 cubed or 125. So this is what Kahle's theorem tells us. So what I want to tell you about in a minute is a wonderful generalization of Kahle's theorem due to Gil Kahle. I think it must have been one of his first papers. Or early papers at least. It's 1983 when this result was published. But I need to give you a little background or 1 or 2 definitions before we can state Kahle's theorem. So some of us think of graphs as one-dimensional simplicial complexes, or simplicial complexes as the natural, higher dimensional generalization of graphs. So I want to tell you what simplicial complex is, in case it's not familiar. So we have a ground set. We think of those as the vertices, just like as of a graph. But in a graph, in a what sometimes people call a simple graph with no loops or multiple edges allowed and without directions on the edges, every edge in such a graph is just a pair of vertices. Every edge corresponds to a pair of vertices, you could say. And here we allow subsets of arbitrary size. And we just have to satisfy a couple conditions. So for convenience, we'll say every singleton, every single vertex is one of the distinguished sets. And then we also have this hereditary condition. I have a typo on this slide. Sorry. If sigma is one of our distinguished elements in our collection of subsets and tau is a subset of it, then tau also needs to be in the collection. So this is this hereditary or kind of closure condition that defines a simplicial complex. And then we call these distinguished elements in our collection of subsets the faces of the simplicial complex. And if one of the subsets in our collection has cardinality k plus 1, we call it a k-dimensional face or just a k face. And that shift by 1 is, just sort of for dimension reasons. A singleton is like a point, and so it corresponds to a 0-dimensional face. Or a pair of vertices, we might think of that as an edge, and like we might think of them as connected by a line segment geometrically. And so that's 1-dimensional. So a pair of vertices corresponds to something 1-dimensional. So in general, if we have a collection of k plus 1 vertices in one of our subsets, then we call it a k-dimensional face. So this what I'm talking about here is sometimes called an abstract simplicial complex. But we can think of it topologically, and we will, via the geometric realization. So we can turn an abstract simplicial complex, which is, again, just kind of a purely combinatorial object. It's just a set and a collection of subsets of that set. But we think of it as a topological space by, it's already suggested by the previous slide, any subset that's in our collection, that's a k-dimensional face, we actually give it the topology of a k-dimensional simplex, or that's homeomorphic to a closed k-dimensional ball. So a subset of size 1 really does correspond to a point topologically, and a subset of size 2, we connect them by a unit interval, say. We can actually do this completely geometrically. If we go into a higher dimensional space, we could have every face of our abstract simplicial complex correspond to a geometric simplex, just the convex hull of a set of points in a Euclidean space. So here's a picture of a geometric simplicial complex, and for example, maybe here's vertices 1, 2, 3, and then so over in the abstract simplicial complex, this corresponds to we had that subset 1, 2, 3 in our collection of subsets, but then we also we must have also had, by the hereditary property, 1, 2, 2, 3, 1, 3, and all the singletons 1, 2, 3. And maybe over here we have 4, 5, 6, 7. And that's another one of our subsets. And so we must have everything underneath it as well. Try something. So that's a simplicial complex. Sometimes authors distinguish between the abstract simplicial complex and its geometric realization. They might even use notation to distinguish between them, but in practice, I think we can kind of use notation or terminology and conflate them, and we will. So we will just think of a simplicial complex as a topological space. So there's one other thing I need to tell you about before we can state Kahle's theorem, which is homology. And if homology isn't really familiar, we could take certainly a 1-hour lecture, or maybe even a few 1-hour lectures, to carefully define it and check some of its most fundamental properties. So this is a 1 or 2 slide crash course in homology, but hopefully it at least gives the feeling for it. For any topological space, we can define homology. Here I'm talking about, you could say, singular homology if you want to know exactly what kind of homology, but we could also think of it as simplicial homology if you know what that is, and those agree for a nice topological space like a simplicial complex. So what is it? If given a topological space X, we take a commutative ring with identity R, then there's a sequence of R modules associated with the topological space called the homology. And these are invariants of the topological space. If we took a homeomorphic topological space, in fact, even if we took only a homotopy equivalent topological space, in other words, one you could deform into, then the homology is the same. So one case that's of special interest to us and in the statement of Kahl's theorem is that the coefficients are the rational numbers. And if you could pick any field of characteristic 0 here, and that would be fine, you would get the same answer, it turns out. Then these are vector spaces. The homology of the topological space are vector spaces. And the dimensions of those are important invariants, and they're called the Betty numbers. So it's just, given a topological space, the Betty numbers are some numbers associated with it. I'm writing it as a sequence, and in principle, that sequence could go on forever. But for a finite dimensional topological space, they only go up to at most the dimension of the space. And after that, they're all 0. So for us today, this is always just kind of a finite list of numbers. And they tell us, how many holes the space has. That's what people say colloquially. So slightly more precisely, Betty 0, the 0th Betty number, is the number of connected components to space, and then the ith Betty number is the number of I-dimensional holes. That's more of a way of thinking of what the Betty numbers are than a formal definition. The formal definition would involve some homological algebra we'd set up a chain complex and take cycles, mod boundaries, and the dimension would be of some vector space, of some quotient vector space would be the homology. But they do seem to kind of tell us something intuitively about the structure of the space, like the number of the holes. Okay. So another special case that's important and is important for us today is what if the coefficients are integers? And this is one of the most important ways people think about homology. There's something called the universal coefficient theorem that tells you homology with integer coefficients is kind of the most rich, or gives you the most information. In fact, if you can compute homology with integer coefficients, then you could compute it with, say any field coefficients or any other coefficients you might be interested in. So somehow it carries the most information, and homology with integer coefficients sees things that homology with other coefficients might miss. So here, instead of vector spaces, we get abelian groups. And the neat thing about abelian groups is that we know the classification of finitely generated abelian groups. There's a free part, and there's a torsion part. There might be a torsion part, which is a finite abelian group. And that does happen for, natural topological spaces that we might be interested in. And it happens for the random simplicial complexes that we'll talk about soon. So here's the maybe simplest topological space that actually has torsion and homology. The real projective plane, its first homology is Z mod 2, the group of two elements. So there is this sort of like finite part to the homology. So, if we say the Betti numbers are detecting kind of how many holes there are in our space, colloquially, maybe torsion and homology is detecting something about the twistedness of the holes or something like that. Again, I only mean that informally. If we want to define things formally, we can set up a chain complex. And in this case, we have a bunch of abelian groups, and we have a quotient group that is a finally generated abelian group. It might have a free part and a torsion part. Okay, so that's a 2-slide crash course in homology. Okay, so now we can define a 2-dimensional hypertree. Kahle called them Q-acyclic complexes. It's defined by the following conditions. It's a simplicial complex that on vertex set n, the numbers from 1 to n, it has complete 1-dimensional skeleton. So what that means is every pair of vertices is one of the subsets in the abstract simplicial complex. So we have all singletons and all doubles. And then we have some 2-dimensional faces. I'll tell you how many in a moment. We have sort of enough 2-dimensional faces so that H1 with rational coefficients is 0, and few enough so that H2 equals 0. And just the number does not determine that, but these two conditions, the H1 and H2 equals 0, does determine the number. So, so somehow we've placed the 2-dimensional faces just right so that there's no homology. This is said to be what Kahle's inspiration was, and what people say still today, over 40 years later, that this is an analog of a tree. A tree is a graph with sort of no topology in various senses. Like one sense is the tree is contractible, can contract it to a single point. Another sense is that it doesn't have any non-trivial homology. The zeroth homology being as simple as possible corresponds to the fact that there's only one connected component, and H1 of the tree being trivial corresponds to the fact that the tree has no cycles. So this is a sort of algebraic topological generalization of trees to 2 dimensions. And it's a natural analog of a tree in some sense. So every two-dimensional hypertree has the same number of two-dimensional faces. It has n-1 choose two-dimensional faces by the Euler formula. The Euler formula we can write it down for any simplicial complex. This is a big generalization of the fact that I think the first place I encountered the Euler the formula is for connected planar graphs. For a connected planar graph, that's embedded in the plane, we know that V minus E plus F equals 2, where V is the number of vertices, E is the number of edges, and F is the number of faces, the connected components of the complement of the graph. But this is it turns out to be a general fact about, homology of topological spaces, or let's say of cell complexes, in this case, that the alternating sum of the number of faces or cells of each dimension is the alternating sum of the Betti numbers. So in this case, that we know how many faces there are of dimension 0 for a hypertree. It's defined to have n zero-dimensional faces. Its vertex set is the numbers 1 to n, and it has a complete one-dimensional skeleton. So as n choose 2 one-dimensional faces. And so if we want to know how many two-dimensional faces there are, then this formula is going to tell us, because there's one connected component, because it has complete one-dimensional skeleton, everything's connected. And then by assumption, it's QA cyclic. So Betti 1 and Betti 2 are both 0. So everything here is known except for F2. And so we can compute the number of two-dimensional faces. So again, every two-dimensional hypertree has n-1 choose two-dimensional faces. The converse does not hold. A simplicial complex with n vertices and n choose 2 one faces, n-1 choose two-dimensional faces might not be a QA cyclic complex, but they do all have the same number of faces. So here's our smallest topologically non-trivial example, a favorite hypertree. I'm drawing a picture of a simplicial complex, and we're sort of cheating to make it a something we can draw. The way we've cheated is we've drawn some of the vertices twice. So vertices 4, 5, and 6 appear more than once, but there's only 6 vertices in this simplicial complex, not 9. And it has a complete one-dimensional skeleton. Every vertex is connected to every other vertex. And then it has 10 two-dimensional faces. And you can see what they are. For example, the 1, 4, 5 is one of the two-dimensional faces, and 1, 2, 5 is one of the two-dimensional faces. So these triangles are all filled in. My favorite way to think of the 6-vertex triangulation of the projective plane is it's the antipodal quotient of the icosahedron. The icosahedron is a familiar polyhedron. It's a Platonic solid with 12 vertices and 20 triangle faces. If you sort of glue antipodal vertices and edges and triangles, you still get a simplicial complex. And because the boundary of the icosahedron is homeomorphic to the sphere, it must be that simplicial complex is homeomorphic to the projective plane, the Zermot-2 quotient of the sphere. Okay, so this, it turns out, if you compute the homology of the projective plane with rational coefficients, it's trivial on dimensions 1 and 2. So it truly is QA cyclic, and it satisfies all the conditions. So for a two-dimensional hypertree. So it's easy to cook up hypertrees that are contractible, just like trees always are. But this is the first example of the smallest example of a two-dimensional hypertree that's topologically non-trivial. It's not contractible. But when, it's like a tree when you look through the lens of rational homology. Through the lens of rational homology, there's nothing happening interesting topologically. But if you look through the lens of, say, integer homology, you see Z mod 2 torsion. And it's not contractible. Okay. So finally, we can state Kahle's theorem. He generalized Kahle's theorem to higher dimensions. So we'll let script T of n denote the set of all two-dimensional hypertrees on the same vertex set. So he gets this formula that if you take the size of the homology and H1 and square it, and you sum all these up over every possible two-dimensional hypertree, then you get n to the n minus 2 choose 2. So this should remind you of Kahle's formula where we got just n to the n minus 2. Now we get n to the n minus 2 choose 2. So first comment is that, so by the way, I should have said a notation. It's a standard thing in topology that if people don't specify the coefficients, they mean integer coefficients. So he means what is the homology with integer coefficients, which might have a free part and a torsion part for an arbitrary topological space. But in this case, it's QA cyclic. So that implies that the free part is trivial. So it's just torsion. And so this is indeed a finite group for this integer homology. And so this is actually a finite sum. So the formula is well posed. And Kahle proved a d-dimensional version of the theorem, but we only need the two-dimensional version for my talk today, so we'll just state it that way. But if you wanted to sum up d minus 1 homology, the order of the d minus first homology for over all the d-dimensional hypertrees, then you would get n to the n minus 2 choose d. It's like, where is all this torsion and homology coming from? How does this actually generalize Kahle's theorem? It does. It turns out that it generalized Kahle's theorem because if you write down the analogous formula for one-dimensional hypertrees, first of all, the one-dimensional hypertrees are exactly the trees. And second of all, now you're looking at the zeroth homology, and there's never any torsion in zeroth homology. And so then those groups are all of order 1. So first of all, it really does generalize Kahle's theorem. I guess, the other thing I'd say about it is that it might be nice to have an enumerative formula for just the number of hypertrees on n vertices, but no such formula is known, and probably no such formula exists. There's been some interesting enumerative work on hypertrees. That the latest I'm aware of is a nice paper of Lineal and Pellet from a few years ago, where they get better lower bounds on the number of hypertrees. So that's just counting things we could call that unweighted enumeration, just enumerating. What Kahle gave was a weighted enumeration. How are we weighting the hypertrees? We're weighting them by torsion squared. And then he gets a beautiful formula that generalizes Kahle's formula. Okay. So that's Kahle's theorem. And now this leads us to our main definition, which was suggested by Kahle's work and also by some work of Russ Lyons, which I'll mention in a minute. So we'll just, rather than saying a random two-dimensional hypertree according to the determinantal measure, I'll just call it a random two-tree for the sake of brevity. We define the probability of each hypertree to be the order of its torsion group and each one squared, divided by n to the n minus 2 choose 2. Well, the formula we just saw on the previous slide of Kahle tells us that if we add all these up over all the two-dimensional hypertrees, it sums to 1. So this is indeed a probability measure. It might be nice, but to know something about just a uniform random two-dimensional hypertree, but you can already guess what seems to be the obstacle to saying anything about the a uniform random two-dimensional hypertree, which is we don't even have very good bounds. That the upper and lower bounds on how many there are far apart. So even if we don't have an exact enumerative formula, we would like to have good asymptotic formulas if we wanted to prove things about uniform measure. Somehow this measure seems quite natural, and in fact, I think work of Russ, Lyons, and this whole subject kind of makes me feel like this determinantal measure is more natural than the uniform measure on hypertrees. So Russ studied in general what he called determinantal measures, and noted that this sort of specific measure was as a special case, and he proved many nice properties about these kinds of measures, including negative association. And for us, we only need a special case of negative association, which is negative correlation of faces. So this is part of a much more general picture. I'll just tell you what we need for our paper for simplicity. So we're taking a random hypertree according to the measure I defined a slide or two ago. What negative correlation tells us, if we pick a random 2 tree and then a list of k potential two-dimensional faces, sigma 1 up to sigma k, the probability that they are all, that those k two-dimensional faces are all appear in our random hypertree is bounded above by the product. So if these were independent events, we would have equality. We would, if they were jointly independent events, we would just be able to multiply the probabilities of the individual events of these faces appearing. They are not independent events, but the inequality always points the same way. They're negatively correlated. So we can also figure out what each of these probabilities is. The probability of any individual face. It's the same for every face by symmetry. Symmetry here, I mean the symmetric group Sn, acts on this probability space. Those are all, permuting the vertices. Those are all, measure preserving transformations. So any face must be equally likely. And we know there's n-1 choose 2 faces in a 2 tree, and there's n choose 3 possible faces. So the probability of any particular face being there is exactly equal to 3 over n. Let me just give you one example of this. So if we pick 4 vertices, 4 numbers from 1 to n, there's a unique tetrahedron that could be a 3-dimensional face there, but consider its boundary, those 4 2-dimensional faces. What's the probability that they all appear in a random 2-dimensional hypertree? Negative correlation tells us it's bounded above by 3 over n to the 4. I mean, in some sense, we already knew that without negative correlation, because in fact, for this special case, the probability is 0. It's not possible to have all 4 faces that are the boundary of a tetrahedron appear, because then that would give a 2-dimensional cycle in homology. That thing is homeomorphic to a sphere, and it's a little, that's a cycle without any boundary. And so that shows up in homology, even with rational coefficients. So the probability of that is 0 because we're taking a random QA cyclic complex. But 0 is clearly less than or equal to 3 over n to the 4. I'm just giving an example of a theorem that always holds. And the theorem is useful because it's so easy to apply. And yeah, and often in the study of random simplicial complexes, we get some global information like homology or something about the fundamental group through careful enough study of local information, like which subcomplexes can appear. So which subcomplexes can appear is something that's particularly easy to study in the Linneal-Mechoulam model. So this is a different model of random two-dimensional simplicial complex defined as follows. We have n vertices again, labeled 1 to n. Again, we have complete one-dimensional skeleton, but now we just put in each two-dimensional face independently with probability p.
Wait, sorry, can I ask a naive question about negative association? So should we just think of this as coming from the fact that the number of one simplices and the number of two simplices is fixed? And so, if I have a triangle here, then it's reduced the number, then the fact that I know it's here has reduced the number of triangles that I could find anywhere else? Or is it like is it some stronger property about the QA cyclicity that is giving us negative association? Like, for instance, if I were to look at simplicial complexes with this number of, one simplices and two simplices, but which were not necessarily QA cyclic, would I still have negative association just as a function of the numbers, or is it actually a property of QA cyclicity?
I hope Russ will chime in if I say anything wrong or incomplete, but I don't even think it's acyclicity. It's more than that. We need the weights, the determinantal measure. So I actually had a correspondence several years ago with Kahle Clivens, who's also studied hypertrees a lot from a kind of enumerative and algebraic point of view, and Andrew, and with Jun He, who knows a lot about matroids and won a Fields Medal. And the question came up: what if we just do the uniform measure on QA cyclic complexes? So again, they all have the same number of faces, but now we're giving them all equal weight. Is it possible that we still have negative correlation there? And even June didn't know the answer to this, apparently. At least that's what it seemed like in the email thread. And then Andrew Newman did a very careful check of all the QA cyclic complexes on 6 vertices and showed that they're not negatively correlated in that case. So if we take the uniform measure on QA cyclic complexes, we lose negative correlation. So it's something about the weights that makes the negative correlation happen. And the reason Russ calls these determinantal measures is, they're coming as determinants of some matrices. So to me, not being an expert on the probability side, it's like black magic that the linear algebra and the determinants are making this negative correlation happen. But I feel sure there's some deeper, reason. But as far as I understand it, it has to do with the weights and not only the numbers of faces or the QA acyclic property.
Okay, so this is just a special case of sort of repulsion and determinantal point processes with distribution kernels, but it's not
something repulsive
if you change the model. Okay, yeah, thank you. That was my question.
So probably the most studied model of random graph, as far as I can tell, and in some ways, the easiest model of random graph to study is the Erdős-Rényi model, where we have independent edges, and independence gives us a lot. So the Linneal-Mechoulam model is the most studied model of random two-dimensional simplicial complex. There's also a d-dimensional version of it that's the most studied model of d-dimensional random simplicial complex, where we take a complete d-1 dimensional skeleton and just put in d-dimensional faces independently, jointly independently. So independence makes the study tractable. And the geometric and topological properties of the Linneal-Mechoulam random 2 complex have been intensely studied for the past about 20 years. I think their first paper about the homology of the random 2-dimensional complex with independent faces appeared in about 2006. they showed the threshold for homology to vanish. And their first theorem is analogous to the Erdős-Rinyi theorem for when the Erdős-Rinyi random graph becomes connected. Somehow the topology of two-dimensional random simplicial complexes is significantly more complicated than the analogous story for random graphs. There's just more that can happen in 2 dimensions. And in particular, the analogs of, the cycle space for a graph, or what we might call the first homology of a graph for a 2-dimensional, complex, or sorry, just the analogs of H0, the space, the number of connected components of a graph. When you go up to H1 of a 2-dimensional complex, all of a sudden there could be torsion and homology. That's much more complicated. And another thing that's more complicated is you have a fundamental group that can even be more complicated than homology with integer coefficients. Now, instead of an instead of an abelian group, it's just a group, and it's usually not abelian. So, and in particular, we know that the threshold for homology to vanish for the random 2 complex and for the fundamental group to vanish are quite different. H1 and Pi1 have very different thresholds for the random 2 complex, and that's part of the story of the topology. But this has been well studied, the phase-independent model of random 2 complex, and the good news of negative correlation is now that we can compare, facts about random hypertrees to, facts about phase-independent random 2 complexes, and that's one of our main methods. So now in the remaining few minutes of the talk, I'll tell you about a few results of Andrew and mine. So the first result is not particularly hard, but I just want to tell you about it so that you get a feeling that the topology of these complexes is quite rich and interesting. It's complicated. It's not only on average that the torsion is large. We could even, strengthen this statement to say with probability tending to 1, the torsion is quite large, which is something that we don't know for the uniform measure on hypertrees. So the expected size of the torsion is exponentially large and n squared. That's one of the theorems in our paper. So here's a more precise statement. Just for comparison, just a deterministic statement that how large can torsion be, period, for a simplicial complex on n vertices. It's bounded above by roughly 3 to the n squared over 4. So this is sort of the same order, at exponentially large and n squared as the largest possible torsion. This upper bound on the size of torsion and homology seems to appear several places in the literature, either explicitly or implicitly. In one place it appears implicitly is Kahle's 1983 paper that we were talking about a minute ago. So, takeaway is torsion and homology is of order as large as it possibly could be. Let me just sketch the proof. Even though we don't know how many hypertrees, two-dimensional hypertrees there are in n vertices, we do have upper and lower bounds, and there's an easy upper bound that's roughly, that's of order, exponential and n squared. And here's the proof. Recall that every 2 tree has exactly n-1 choose 2 two-dimensional faces. Then we have this upper bound, big binomial coefficient, n choose 3, choose n-1 choose 2. And you can just kind of repeatedly apply Stirling's approximation for factorials and simplify this, and eventually you get something like en over 3 to the n-1 choose 2. So actually, maybe we only need to apply it once. This is a pretty simple upper bound, but it's good enough for what we want to prove. Every two-dimensional hypertree has n-1 choose 2 faces. So there's at most n choose 3 choose n-1 choose 2. This seems like a silly upper bound because most simplicial complexes with this many two-dimensional faces are not going to be hypertrees, but nevertheless, it's a good enough hyperbound. It's a good enough upper bound for what we want to do. Somehow it's the right order, in the sense that it's the right size of exponent. What's wrong and why this is a big overestimate is this number probably is too big. But okay. So then the other ingredient is just, sort of basic inequality chasing. For non-negative numbers, x1 up to xk, we can always bound the sum of their cubes by something in terms of the sum of their squares. And, this follows from Jensen's inequality because x to the 3/2 is a convex function on the, non-negative reals. Okay, so then we can kind of put those things together to, try to sketch the proof. First of all, just definition of expectation. We just sum probability of each event times the, order of torsion, homology. And, to go from here to here, we apply Kahle's theorem. Or no, well, really, this is just the definition of our measure, that the probability of any given event is the order of torsion, the order of the homology group squared divided by n to the n minus 2 choose 2. Kahle tells us that's a probability measure, but I'm just reminding you what that definition was. So since we get torsion squared and we already had one torsion there, now we've got torsion cubed. So now we want to apply that lemma that allows us to bound, the sum of cubes of something in terms of the sum of squares. And then, we get some formula. We apply Kahle again once we have the sum of torsion squared, because he tells us how big the sum of torsion squares is. So we apply Kahle again. And then, we've got something that's just, formula in terms of n that we can simplify. And eventually we get this. Okay, so one can refine this and consider the second moment and things like this, and say not only can we say something about expectation of torsion, but we can say with high probability torsion is exponentially large in n squared. So we investigate other topological properties of the random 2 tree, and one of the things we show that I don't have much time to tell you about is that the fundamental group is asymptotically almost surely Gromov hyperbolic. I won't define Gromov hyperbolic in the sense of time, but you can think of it as like sort of a negative curvature property. And here, asymptotically almost surely, I mean the probability is approaching 1 as n, the number of vertices, tends to infinity. So for this, this depends on earlier work of my advisors and me on fundamental groups of the face-independent model. And when we combine that with a negative correlation of Lyons, we actually get a short proof. That one of the main ideas in this is Gromov. We can define hyperbolic in terms of isoperimetry, and Gromov tells us that if we can get a local isoperimetric inequality, then we can get a global isoperimetric inequality, perhaps with a worse constant, but we still get hyperbolicity. So in other words, that one thing people say in this business is, it suffices to check hyperbolicity on balls of finite radius. Even that requires some work. We need an important lemma from this earlier paper with Babson and Hoffman that says we get an isoperimetric constant if we can handle the ratio of 2-dimensional faces to 0-dimensional faces, on any given set of vertices. And then, but that follows from negative correlation because then we just have to check, it's like a subcomplex count, just like what we did for tetrahedrons, but we're counting all subcomplexes with a certain number of faces. It doesn't even matter how many subcomplexes there are because there's only finitely many subcomplexes with a given number of faces, and because we only have to go up to balls of, to a certain size. thanks to Gromov, local to global principle. So we get some handle on the fundamental group. And then we also showed topologically interesting fact that a typical random 2 tree is aspherical. Again, asymptotically almost surely, the probability is 10 to 1. So in that sense, that projective 6 vertex triangulation of the projective plane is a little misleading. Somehow that's not what a typical hypertree looks like. They typically do have torsion and homology like that one, but what this says is they typically have a contractible universal cover, and RP2 certainly does not have a contractible universal cover. Its universal cover is the sphere, so it is not something that's aspherical. And this is something that is, the proof here is similar to hyperbolic, the proof that the fundamental group is hyperbolic, where we just need to rule out some family of forbidden subcomplexes, which we can do with negative correlation. So these proofs in this paper are quite short and self-contained. Some of them depend on some lemmas or theorems from earlier papers, and this one including some earlier work of Costa and Farber. But if we use those as black boxes, then the proofs of all these topological facts about two-dimensional hypertrees are quite short, just one page or 2 pages each. Okay, so let me close with a couple of open questions. We can think of the random two-dimensional hypertree as an analog of uniform spanning tree and a complete graph. Uniform spanning trees and complete graphs are very well studied. And one of the most remarkable facts about them is that if you properly rescale them, they have a scaling limit. It's a random fractal called the continuum random tree. This was, as far as I understand it, introduced and studied deeply by Aldous, and maybe in the 1980s, and continuum random trees continue to be studied. So that's the one-dimensional story. Even the uniform spanning tree in a complete graph has a quite interesting geometry and structure in the limit as n goes to infinity if you properly renormalize. Is there an analogous story in 2 dimensions? I don't know. And I mean that in a very open-ended way. I don't know what the right notion of scaling limit is, how to rescale them, or what kind of convergence. This kind of convergence, I guess we can think of Gromov-Hausdorff sense, for example. But I'll tell you one other open problem about random 2 trees and their fundamental groups that I've gotten interested in. It seems that the fundamental group of a random 2 tree is a candidate for a one-ended hyperbolic group without surface subgroups. So what do I mean by surface subgroup? Something that's studied a lot in geometric group theory is the fundamental groups of orientable compact surfaces. So for a surface of genus 1, that's the torus, and its fundamental group is Z cross Z, the free abelian group on 2 generators. Certainly pi1s does not have any subgroups corresponding to Z cross Z, and the reason is it's well known in geometric group theory that such groups, that a hyperbolic group cannot have such a subgroup. It's a poisoned subgroup. So you do not have any Z cross Z subgroups. But all the higher genus subgroups are possible. All the higher genus surfaces give possible surface subgroups. It's a long-standing question of Gromov whether every one-ended hyperbolic group contains some surface subgroup. This was proved for hyperbolic 3-manifold groups. So if you have the fundamental group of a hyperbolic 3-dimensional manifold, Kahn and Markovich proved this, celebrated work, but somehow those seem to be very special kinds of hyperbolic groups. And in general, is it true that every hyperbolic group, at least the ones that are one-ended, which is somehow most of them from the point of view of randomness, for example, is it true that they all have surface subgroups? I don't see any reason why that should be the case. So this might be a good candidate counterexample. I'll just mention there's another model of random group that's quite well studied, the Gromov's density random groups, and those do have surface subgroups. This was showed by Alden and Kahle, and that they studied the density random group. But those groups those random groups are really random presentations of groups. And if you write down the presentation complex, which is a cell complex that has the right fundamental group, the group that you want, those things are also aspherical. But geometrically or topologically, the way Alden and Caligari, or sorry, it's Alden Walker and Danny Caligari. Caligari and Walker showed that they have surface subgroups is they actually find surface subcomplexes of the presentation complex. They find surfaces living in there and then show that the fundamental group maps injectively into the presentation complex. So the reason these hypertrees are appealing to me for this question is that can't happen here. They're still aspherical, but you're not going to find surface subcomplexes of the two tree because it's QA cyclic. There's no surface subcomplex there. So if there's a surface subgroup of the fundamental group, it's for some other reason. So this is, one candidate for, a good application of the probabilistic method. And in general, I think, random simplicial complexes seem to give interesting and extremal examples of simplicial complexes that we don't know how to construct explicitly. And various models of random groups seem to be good candidates for, or at least plausible candidates for, examples and counterexamples in geometric group theory. And I think this is a good place to stop. Thanks everyone for your time and attention. And thanks to this various funding agencies that helped support this work 5 years ago or so.
Okay, let's thank Matt for this very interesting talk. Thank you, Matt. So let's say we'll start András's talk in 10 minutes. So at 10:08, just to give everyone a break. And during that break, we'll have questions. So, okay, I have some, but let me first ask if anyone else has any others.
I have a question. Matt, when you talk about a scaling limit at the end, do you have any suggestions about how that could be? Because if you use any natural metric, it seems the diameter is always 1.
Right. So maybe we don't need to rescale on the metric. I guess one thought is maybe, so by thought, I mean, this is sort of a half-baked pipe dream that I've had without having really thought about it carefully. But what if the convergence is not just as metric spaces, but as metric measure spaces, and we keep the metric so that the diameter is 1, but what we rescale is kind of the measure, like the area of each two-dimensional face now, instead of making that 1, that scales down as 1 over n squared or at whatever rate. I'm not sure. I would really love to see some kind of limiting random fractal behavior or something like analogous to the uniform spanning tree on the complete graph, the continuum random tree. But I've never thought about it carefully enough where I even have a a candidate definition or a conjecture in that area.
Okay.
Other questions?
I see Ali and
Yeah, I see some
Andre
raised
have answered them.
yeah,
So
so
I
if you
have
guys
a
want to just
concern.
unmute yourselves. Okay, I think I hear someone talking.
Yes, I'm asking if there is a local algorithm to construct such a random two-dimensional tree or not.
Is the question, is there an algorithm to construct these? That's a great question, and there is. Well, again, maybe Russ will correct me if I say something wrong or incomplete. But work of Russ on determinantal measures, I think, already implies some reasonably fast way to sample these. I think sample them. Actually, Russ's algorithm will let you sample them from the correct measure, and I think in polynomial time. But there's other approach and what people might do more in practice, and what seems to be faster when my collaborators and I have done experimental work in this area is to sample with Markov chains. So you start with one, hypertree, and then, try to do something like a Metropolis Hastings algorithm where you, add face and delete a face so that you still have a hypertree, and maybe you weight things according to torsion. So for a long time, this kind of Markov chain was expected to converge quickly, but my understanding is it wasn't known. But now, thanks to work of Junhe and others on the algebraic combinatoric side, now there's work by Cynthia Van Zandt and her collaborators that implies that these Markov chains actually do mix, in reasonable time. So I think everybody kind of believed that they did, but now that's known. So in practice, this seems to be quite fast and quite efficient, that you can just start with your favorite hypertree, and there's some easy examples you can take. Like you take a complete skeleton of one dimension. So for a two-dimensional example, start with a complete graph on n-1 vertices, and then take the cone with the nth vertex. That's a contractible hypertree. So it is a hypertree. It's not interesting topologically, but it does count as a hypertree. And then you can just use that as the starting point for a Markov chain where you add faces and delete faces randomly. And that seems in practice, and now is known theoretically, to converge quickly to the right stationary distribution where things are weighted by torsion squared. So
Okay, thank you.
but there are algorithms for simply.
I mean, something like Wilson's algorithm, which give exact simulations. So there is not a known algorithm like that.
I'm having trouble hearing you. I don't know if you can make your
It's
voice.
something like Wilson's algorithm, an a sort of local exact sampling algorithm.
Right. This is something many of us in this area have wondered for years. If there's an analog of Wilson's algorithm, that would be quite lovely if there is. And we've never found anything like that. I think Russ suspects that there is no such algorithm, and I think he would be the expert. But many of us have tried, and it would certainly be delightful if there were an analog of Aldous algorithm or Wilson algorithm for sampling hypertrees, even according to the uniform or according to the more natural determinantal measure. So far, we don't have anything like that.
So let me add to what you said. So you were talking about the Feder-Mihail conjecture without that name about fast mixing in matroids, which, as you said, has not been proved. However, as far as I know, that's just for the uniform measure, not for these determinantal measures or other measures.
I see. So that is a good way to sample according to uniform measure, but it's not known for the determinantal measure. Okay, so I should be more careful.
Yeah, but that in fact also gives you a way to compare via simulation the uniform to the determinantal measures to see what differences there may be in some of these statistics.
Okay, that's great. I see a hand up, Andre.
Thanks. I will be probably short. This is just to add to this scaling limit debate that you mentioned. Probably you know it, but there is a paper by Bamidi, van der Hofstadt, and Sen, who derive scaling limits in Gromov-Hausdorff topologies, and the limit is inhomogeneous continuum random trees you already mentioned. Could this be used also in your case? This is the question.
Right.
Their paper, because it's, yeah.
I think that's a very nice question, and I don't know the answer, but I think there's probably something to do in this area.
Okay, maybe this could be useful. Yeah. Then
Thank you.
Thanks.
Any other questions? All right, well, thank you, Matt, again for the talk. And okay, I guess we have a couple of more minutes before András starts. So maybe if you want to steal the share.
If you want to use the meter.
All right, so it's 10:08. So let's start the next talk. So we're very happy to have for our second talk, András Mészáros, who's going to be telling us about determinantal hypertrees and graph limits.
Thank you. Thank you for the invitation, and thank you, Matthew, for the nice introduction to determinantal hypertrees. So we will start by describing a higher dimensional generalization of Grimet's theorem. So Grimet's theorem answers the following question. So let Tn be a uniform random spanning tree of the complete graph on n vertices, and let us choose a vertex On uniformly at random from all the vertices of Tn. We call this vertex On the root. And then take a positive integer r, and we call this r or radius of psi. So what we do, we consider this vertex On the root and consider the r neighborhood of this root. That is, we consider all the vertices of the tree which are at distance at most r from the root, and consider the subgraph induced by these vertices. And so this way we get a rooted graph. And the question is that what is the asymptotic distribution of this of this R neighborhood of the root? And this question can be answered with the help of a infinite random rooted tree, which is often called the skeleton tree. So this is defined as follows. So we take a sequence of independent Galton-Watson trees with Poisson-1 offspring distribution. Note that these trees will be finite with probability 1. And then we take we connect the roots of these trees with a semi-infinite path like this.
Can you remind us what a Galton-Watson tree is?
So each vertex will have a random number of children, where the number of children is given by a Poisson-1 random variable, and all these choices are independent. Okay, and then we have this tree, and we choose the root of the leftmost tree as the root of this graph. So what we have here is a random infinite tree together with a distinguished vertex, which we call the root. Okay, this is the skeleton tree. So now we are able to state Grimet's theorem, which again the setting is that we take a uniform random spanning tree, and we choose a root On uniformly at random. And also we have the skeleton tree, and then we take a finite rooted tree of depth r, which means that all the vertices at most distance r from the root, and there is at least one vertex which exactly at distance r. Okay, and then we can take this probability that the r neighborhood of the root in Tn is isomorphic to this fixed rooted tree TO, and these probabilities will converge to the probability that the R neighborhood of the skeleton tree is isomorphic to this rooted tree TO. Here we are speaking about rooted isomorphism, so we need a graph isomorphism which also preserves the root. Okay, so we have this statement. So the local weak limit of uniform random spanning trees is given by the skeleton tree, and note that this statement is also true in a quench sense. So we can condition on the tree, and then this conditional probability will give us a random variable, and this random variable converge in probability to the probability that the R neighborhood of the root in the skeleton tree is isomorphic to TO. Okay, now we will describe the higher dimensional analog of this theorem. So we will define a notion of local weak limit for simplicial complexes, in particular for determinant hypertrees. So let us consider a k-dimensional simplicial complex C, and we define a bipartite graph GC as follows. So the two color classes of GC are the set of k faces, the set of k-dimensional faces, and the set of k-1 dimensional faces of C. And a k-dimensional face is connected to a k-1 dimensional face if and only if it contains it. In other words, this graph is just the Hasse diagram of this simplicial complex restricted to the k-dimensional faces and k-1 dimensional faces. And also one can note that all the k faces have degree k-1. Okay, and by choosing a uniform random k-1 face as the root, this graph GC can be turned into a random rooted graph GC OC. Okay, so basically, if we start with a graph that is with a one-dimensional complex, then this bipartite graph is obtained by simply subdividing each edge with a vertex. Okay, so this is, in this sense, really just a generalization of the one-dimensional case. Okay. And now we can state our theorem. So let T and K be a k-dimensional determinant hypertree on n vertices, and let G and O n be the corresponding random rooted graph, which we defined on the previous slide. And then these random rooted graphs converge to some random rooted tree, which we call the semi-k-ary skeleton tree. And again, this convergence, this local convergence means that the probability that the R neighborhood of ON in the graph GN is isomorphic to some fixed rooted tree TO converge to the probability that the R neighborhood of the root of this semi-k-ary skeleton tree is isomorphic to TO. Okay, so note that here these graphs G and ON are no longer trees itself, but they are locally tree-like, so their local weak limit will be a tree. Okay. So now in the next slide we will describe this limiting object, the semi-k-ary skeleton tree. Okay, so what we do, we start with the root, and the root will have a random number of children, where the number of children is given is 1 plus a Poisson k random variable. Here k is the dimension. Okay, and then actually we will not only generate these three, but in the process we will also generate a perfect matching of these three. So what we do here, we choose a child of the root uniformly at random, and we match this child to the root. So we will we denote this by a red edge, and then we consider the vertices in the first generation. Then note that these vertices actually correspond to k faces. So these vertices must have degree k plus 1. So this means that all of these vertices here must have k children. So in this picture, k is 2. This is the two-dimensional case. Okay, and then we do the matching part. So if we have a vertex here which is unmatched, then we choose a child uniformly and random, and we match this vertex to this child. But if a vertex is already matched, then we do nothing. Okay, so here we added these edges to the matching. Okay, and then we move on to the second generation. Okay, these vertices will have a random number of children. So if a vertex is already matched, then the number of children is just given by a Poisson k random variable. But if a vertex is not unmatched, then the number of children is given by a 1 plus Poisson k random variable, and so on. So all these choices are independent here. Okay, and then we proceed with matching the vertices. So if we have an unmatched vertex here, then we match it to one of its children, like this. And note that on the previous slide, if a vertex was unmatched, then the number of children is 1 plus Poisson k. So unmatched vertices always have at least one children. So we can really choose a uniform random child to match with this vertex. Okay, and this process goes on to infinity. This way we will get this random rooted tree, and this will be the limit. Okay. This describes the local weak limit of this simplicial complex. Okay, and it turns out that there is another random complex which has the same local weak limit. And
Wait, sorry, can
this
I ask
is
a question? So for the previous
yes.
complex, so when k is 1, this should give you this infinite tree in Grimm's theorem. So just to
Yes.
make sure I understand, this is because, so okay, in your second layer where here k is 2, if k is 1, you'll just get a single edge. And so you
Yes.
can kind of ignore that. But then you will have chosen a distinguished child wherever the first matching went. Here it's
Yes.
your third child, I
So
guess.
that's why
And so
we
that
will
will be
have this infinite path here
right,
that
exactly.
correspond to
Your
this
choice of that
unique end
distinguished
of
child.
this tree.
Okay, just making
Thank you
sure.
for the question.
Yeah.
Okay, so we have this other complex, the one out D complex. So this is defined as follows. So we start with the complete D minus 1 skeleton. That is all the D minus 1 dimensional faces are present. And then for each D minus 1 dimensional face F, we independently choose uniformly at random a vertex from the vertex V from the vertices that are not contained in F, and then we add the face F union V to the complex. Okay, and the local weak limit of these complexes were determined by Linear and Pellet before my work, and it turns out that these complexes have the same local weak limit as determinantal hypertrees. And in many other sense, these one-out complexes seems to be very similar to determinantal hypertrees. So that's why I came up with this conjecture, which might be true that there should be a coupling of this one-out complex and determinantal hypertree and the determinantal hypertree such that their symmetric difference is small with high probability. Okay, but you can ask why do we care about the local weak limit of complexes? Well, as an example, let me mention a result of linear and pellet. So this result is about the linear mesh-lamp complex that Matthew already introduced, but let me repeat the definition. So this is a random d-dimensional simplicial complex on n vertices with complete d-1 skeleton, and each d simplex is added with independently with probability Pn. Okay, and the theorem of linear pellet is about the sparse case where this probability Pn is chosen as C over n, where C is some fixed constant. And they proved that the expected dimension of the D's homology group over the reals, appropriately normalized by n choose D, this will converge to some explicitly given constant, and that actually this convergence is also true in probability, not just in expectation. Okay, and here is a brief outline of the proof of linear and pellet. So they consider an n choose D times n choose D matrix Ln, which we can call Laplacian. So this is defined by multiplying the D's boundary matrix with its transpose. And then we can define this measure mu n, which is just the empirical measure on the eigenvalues of Ln. It is just the uniform measure on the eigenvalues of Ln. Sometimes I will call this measure the spectral measure of the simplicial complex. Okay, and then the expected dimension of the D's homology properly normalized is equals to the normalized expected size of the kernel of Ln plus some constant, and this normalized dimension of the kernel of Ln actually can be expressed as the expected measure of the atom zero at this measure nu n. And the key observation of linear and pellet is first of all these linear mesh-lamp complexes have a local weak limit which can be nicely described, and from this fact it follows that these spectral measures, the expectation of nu n, actually will convert weakly to some limiting measure nu. Okay, and from this weak convergence, it follows that the lim sup of the expected measure of zero with respect to nu n is at most the measure of zero at the limiting measure. Okay, and then linear and pellet goes on and analyze this limiting measure nu, and they are able to give an explicit formula for the measure of the atom zero. Okay, and so this way we get an upper bound on the lim sup of this normalized expected normalized dimension, and then they using other methods they give a matching lower bound. This is based on something called a collapsing process. Okay, so this was a motivation why we care about the local weak limit of random complexes. Of course, one could get the idea to apply the same idea for determinant hypertrees, but note that in this case we don't get anything meaningful because by definition the real homology of determinantal hypertrees is trivial. Okay, so it's not that interesting, but there is a possible application, namely one can conjecture that for any d, if we take the expectation of the logarithm of the size of the d minus 1 homology group of a d-dimensional determinantal hypertree and normalize it by n choose d, then this limit exists. So actually, Matthew just gave a proof that if this limit exists, then this must be positive. Okay, so this is kind of in Matthew's talk we have seen that this is the right normalization of this quantity. Okay, and so but this thing here can be expressed in terms of the spectral measures. So again, let nu be the empirical measure on the eigenvalues of this ln, this Laplacian, and it turns out that this normalized expectation of the log of the size of the homologic group can be expressed as 1 over 2 times the integral of log t with respect to the expectation of nu n plus some smaller term. So
Sorry, could you say more about the relationship between these weak local limits and the empirical spectral measure? So you in the previous slide, like why is a weak local limit enough to get the full empirical spectral measure? And does it matter that the weak local limit is the specific explicit thing, or is this just a general property if you know the weak local limit?
it's just a general property. So
Okay.
basically this even if you just given a matrix, then okay, first you have this uniform measure on the eigenvalues. Okay, but actually you have also have this spectral measure corresponding to each kind of choice of for each choice of vector you have a corresponding spectral measure, and you have the orthonormal basis, and then if you and for each basis vector you have this local spectral measure, and if you average out these measures, then you get the uniform measure on the eigenvalues. Okay, and kind of these matrices, this matrix Ln is very sparse. So this has this local graph-like structure. So this is really this boundary map is just kind of the adjacency matrix of that bipartite graph. So basically, to understand this local spectral measure up to some precision, you need to just understand a large enough neighborhood of the given vertex.
Yeah. Okay.
This is really kind of a standard by now a standard technique in graph limit theory.
Okay. Thanks. And then, could you say a little bit about where this equality you have here that?
Okay. Basically, this okay up to some thing. This homology group is basically just the determinant of this matrix Ln, or the determinant of this boundary map of this boundary map, and we
Okay, so you're
multiply
just
this
using the fact
boundary
that the
map
log
with
of the
it.
determinant.
So there is this 1/2 because we kind of spare the determinant here when we multiply it. Okay, but of course these are not really square matrices because they have a and so we have some multiplicity of 0 which cause some minor trouble. So like for example here we only need integrate over the positive the real line, the positive half of the real line, because of course log 0 doesn't really make sense. Okay.
But basically this just comes from the fact that the log determinant is the sum of the logs of the
eigenvalues, yes.
the absolute value of the
Yes,
eigenvalue. You have to do some error analysis. Okay, yeah, this makes sense. Thanks.
Okay, so again we have these expected spectral measures convert weakly to some measure nu, and this weak convergence actually by definition means that for every bounded continuous function f, the integral of ft with respect to this expected spectral measure nu, and this integral will converge to the integral of ft with respect to the limiting measure. Okay, and to prove this conjecture, what we need it would be nice to also prove that this convergence of integrals for the function log t in place of f, but of course it's not that simple because log t is not a bounded function. Okay, so the weak convergence of these measures is not enough. We need something stronger. We also need a good control of the behavior of nu n near 0. So what we need is basically some sort of spectral expansion for these random complexes, but actually a weaker assumption is enough. Okay, but this is just a possible application, even for determinant hypertrees. Okay. So we see that we can use these spectral methods and these sparse graph limit methods to understand the homology of determinant of random complexes over the reals, but these spectral methods are not available over finite fields in positive characteristics. So to understand the mod P homology of random simple shell complexes, we need some other tools, and one such and one possible tool is, as I will show you, is to use dense graph limit theory. So here I mentioned two conjectures. So one is about the linear Mesulam complex, which says that if we consider the normalized expected dimension of this homology of the linear mesh element complex, but over the p element field, then this normalized dimension will still converge, and it will converge to the same constant as in the real case. Moreover, we have this conjecture for for determinantal hypertrees that for two-dimensional determinantal hypertrees that the normalized dimension of the first homology over FP should converge to zero in probability. In fact, we have even stronger conjectures. So by Kahle and Newman. Okay. So I managed to prove this statement in the special case when p equals 2. So our theorem is that this the dimension of the first homology group of a two-dimensional determinantal hypertree over with F2 coefficient. If we normalize this dimension by n squared, then this will converge to zero in probability. Okay, and it is easy to see that actually it is enough to prove that the logarithm of the expected number of mod 2 cocycles, one-dimensional mod 2 cocycles, normalized by n squared will converge to zero. Okay, but now let me try to rephrase this formula in more graph theoretic terms. So one cochains with F2 coefficients just correspond to functions from the edge set of the complete graph to the two-element field, and any such function is actually uniquely determined by its support. So actually the one-dimensional cochains over F2 can be identified with graphs on n vertices. Okay, and then we can consider cocycles, and the cocycles will correspond to graphs such that every triangular face of a random determinantal hypertree contains an even number of edges of G.
And so is G just the graph of
Yes,
where of the edges where your function takes value 1 rather than 0?
Yes, the G is just the support of this function f, which is a one cochain. Okay. Okay, so let us introduce some notation. So we use PG for the probability that the cochain corresponding to the graph G is actually a cocycle. And okay, and as we have seen, this is just the probability that all the triangular faces of the determinantal hypertree contains an even number of edges of G. Okay, and let us consider the Erdős-Rényi graph with edge probability 1/2. This, in other words, we just consider a uniform random graph on n vertices. Okay, and then this quantity here can be written as follows. So first of all, this expectation, the expected number of cocycles can be rewritten as a sum, namely a sum over all graphs G, this probability PG. Okay, and of course this sum here can be rewritten again as a expectation over a uniform random graph, or in other words, over an Erdős Rényi graph. So this sum is just 2 to the n choose 2 times the expected value of P, of the P of an Erdős Rényi graph. Okay, and then note we try to bound this expectation. Of course, this expectation for any choice of u, this expectation is at least e to the minus u times n squared times the probability that the p of an Erdős Rényi graph is at least e to the minus u times n squared. So this is trivial, but with some work, one can see that this is not only a lower bound, but at the cost of a little of one term, this is actually also an upper bound on this expectation. Okay, and with some algebra, we can rewrite this expression like this. So what we got here, this is the interesting part here. So we have some normalized slope of some probability. So this expression here really looks like an expression from some sort of large deviation principle. Okay, so what we need here is some sort of large deviation principle for the Erdős Rényi graph. And such a large deviation principle was proved by Chatari and Varadan, and their result actually relies on the language of dense graph limit theory. Dense graph limit theory is a huge area of graph theory. Now it was started by Lovász and Szegedi, and kind of the key idea is that if we have a sequence of dense finite graphs, then often this sequence can be replaced with some more analytic limiting object, and then we can work on this analytic object and use more analytic tools and prove something, and then we can pull back these results to the finite setting. Okay, so in this case, this analytic limiting object is something called a graphon. So a graphon is simply a symmetric measurable map W from the unit square to the unit interval. Okay, and given a graph on n vertices, we can define a corresponding graphon, which will be simply just a continuous version of the adjacency matrix. So here we have a formula for this, but what happens if we have this unit square, and then we subdivide this unit square into n squared smaller squares, okay, like a grid, like an n by n grid, and then this graphon WG will be constant on each of these small squares, and then this constant will be either 0 or 1, and if we have a small square, then this value is actually given by the corresponding entry of the adjacency matrix. Okay, but here we have a formula for this. Okay, and one can define a nice metric on the space of graphons, which turns the space into a nice compact metric space. Okay, I'm lying a little bit because to get a compact space, actually we need to factor out this space with some equivalence relation, which actually corresponds to just permuting the vertices of the graph, just relabeling the graphs. Okay. Okay, so we define graphons, and now we can state the large deviation principle of Chaudhary and Varadhan. So for any W, which is just a real number between 0 and 1, we can define this function. And then for a graphon W, this IW, this rate function IW, is defined as the integral of I of WXY over the unit square. Okay, and we really have a large deviation principle. So if F is a closed subset of the space of the graphons, then we can take 1 over n squared times the logarithm of this probability that if we take an Erdős-Rényi graph on n vertices and take the corresponding graphon, then this graphon is in this closed set F. And this and the lim sup of this expression is bounded by minus the infimum of this rate function on this closed set F. Okay, so this is the really how a large deviation principle looks like usually. Okay, and now we can finish our proof. So recall that we had this expression for the Erdős for the normalized logarithm of the expected number of cocycles, and here we still have this function p, which is hard to compute exactly, hard to understand, and it's not clear how one can extend this function to the space of graphons. So what we do that we can find a specific upper semi-continuous function f on the space of graphons that kind of serves as a sufficiently nice upper bound for this function pg. So what we have is that the log of pg for any graph t, the log of pg over n squared is at most f of the graphon corresponding to this g up to some small order errors. Okay, so basically in this formula above, we can replace this p by this f, and then we get this formula on the bottom of the page. Okay, and here what appears here is really something where we can apply the large deviation principle. Okay, this is because, of course, this set Fu, which consists of all the graphons where graphons W, where Fw is at least minus u, is closed by the upper semi-continuity of F. So we can use the large deviation principle to bound this probability here. And of course here there is still a non-trivial fact to have a strong enough bound on this infimum. Okay, so and this really depends of course on the specific choice of our function f. So I won't be able to give any details, but this infimum here can be bounded using some information theoretic inequalities. Okay, but now let me say a few words about how this function f is constructed. So basically the construction of f is based on the following inequality. So the log of this function pg is at most n minus 2 times log n plus 1 minus 2 over n times this sum over all edges of the complete graph, this log of tgij over n. Okay, here this tgij is just the number of triangles ijk containing an even number of edges of G. Okay, so given an edge ij, we can choose like n. We can choose a third vertex in n minus 2 ways, and we count those cases where we get a triangle which contains an even number of edges of G. Okay, and if we consider this sum here, this sum of this logarithm, actually it turns out that this expression, we can make sense of this expression even for graphons, not only for graphs. Okay, so basically we can make sense of this expression for also for graphons, and it turns out that this way we will get an upper semi-continuous f, and that's good enough. And then also this bound here is strong enough that it allows us to get the upper bound 0 on this expression. Okay, so and again we are in the case where, so if we consider the one-out complex instead of determinal hypertrees, then that complex actually satisfies a very similar inequality, just some of the constant here or some of the lower order terms are different, but basically we have a very similar inequality, and basically because of this the whole proof goes through, and we can prove that the normalized mod 2 homology of the dimension of the normalized dimension of the mod 2 homology converges to 0 in probability also for the one-out complex, although for the two-dimensional one-out complex. So again, we see that one-out complexes and determinal hypertrees are very similar. Okay, and of course it's natural to ask whether we can extend this proof to the case of OWPS, which seems completely possible, but to do this we also need to build some of the tools. So we need to come up with some generalizations of graph limit theoretic notions, so we can have generalization of these large deviation principle and so on. So there is some work to do here, but it seems possible that we can generalize this method for odd primes too. Okay, and finally, in the last two slides, let me mention more precise conjectures about the distribution of p-torsion of hypertrees or just. So let P be a prime, and Kahle and Newman conjectured that the dimension of the first homology group with FP coefficients will have a limiting distribution without any normalization. So this homology group is so small that we don't even need to normalize it to get a limiting distribution, and more precisely they have this formula for the limiting probability that the the first homology group over FP has dimension K. Okay, in fact, they had an even finer conjecture, namely, they conjectured that for any finite abelian P group G, the probability that the P torsion part of the first homology group is isomorphic to G, well, in the large N limit, this is proportional to the size of the automorphism group of G. Okay, and this distribution here on the right hand side is called the Cohen-Landstra distribution. So this came up first in the conjectures of Cohen and Landstra on the class group of quadratic number fields, but this since then this distribution here also appeared as the universal limit of cokernels of a large class of random matrices. Okay. But actually this conjecture of Kahle and Newman is false for P equals 2, but there are some indication that this P equals 2 case is somewhat special, so it still might be true for larger primes. Okay, and so the main difficulty of understanding determinantal hypertrees or in general random simplicial complexes from a random matrix point of view. So from a random matrix point of view, we need to understand the boundary maps of these matrices of these complexes. Okay, and these matrices kind of do not have enough symmetries. So these matrices have some very rigid structure, and somehow the lack of symmetries makes it difficult to understand these matrices. Okay, so I consider the related model, which is really inspired by determinantal hypertrees, but this is a model which has more symmetries, and kind of we can take advantage of these symmetries, and for this model we can prove that the cokernel of this random matrix indeed follows this Cohen-Landstra distribution, at least for P at least 5, but I won't give any details. So just the point that I wanted to make, that really the lack of symmetries of these random matrices that makes understanding them very difficult. Okay, thank you for the attention. Any questions?
Right. Thank you very much for that very nice talk. Yeah, does anyone have any questions? I see a raised hand from András Rakar.
Thanks. Thank you. It was a great talk. Just a short question for this ending. Are there any relates to which this novel, if I understand you correctly, random matrices could be related to? Are they related to any ensembles or so to any known type of random matrices? Thanks.
So again, this is a very niche area of random matrix theory. So this cokernel only makes sense for matrices with integer entries, or in more general setting like matrices where the entries are coming from the p-adic integers and so on. So these are the two cases that considered, and of course the classical matrix ensembles are all these all have these Gaussian entries and so on. So kind of yes, but it's an interesting area, and it's kind of, yes, so yes, but even in this area, we have a universality phenomenon which can be considered as some kind of periodic analog of the universality of the spectrum of Wigner matrices and so on. But there is no direct connection between there is no formal connection between these two things, but it seems like it's a good thing to think of the co-kernel as some sort of analog of the spectrum.
Mhm. And what kind of limit methods to study here? You have this theorem for p greater than 2. What kind of limit for these objects at the end could be used? Probably not Grotons, but what you mentioned.
Sorry for this last slide. So here for this last result, we do not need to rely on any graph limit theory. So this result is well, basically this is something like an integrable system. So here we can very precisely calculate everything. And yes, basically on the way we need to make some estimates, and these estimates are usually rely on some sort of inequalities from information theory.
Okay. Thank you.
So what goes into the proof of this is a lot of linear algebra and a little bit of information theory.
Thanks a lot.
And of course, this thing called the moment method of Wood, which is the very standard tool to understand these random abelian P groups.
Other questions? So I guess I was curious, maybe I asked you this before and then forgot, but so okay, you've shown that the Kahle-Newman conjecture is false for p equals 2. Do you believe that it's true for all odd primes, or do you think there could still be issues for, let's say, p equals 3?
So no, it's so this conjecture is false because cochains where the support is given by a pentagon tends to appear with sufficiently high probability. So we have these kind of cocycles with very small support with support of constant size. But I know I have a proof that this phenomenon only occurs when p equals 2. So if p is odd, then with high probability we don't have any one-dimensional cocycle with constant size of support. Okay, so this is kind of an indication that the case of OP might be different.
I see. So at least the obstruction for p equals 2 does not happen, but there could be another obstruction that you haven't seen yet.
Yes.
Okay.
Does this give any suggestion for a way to correct the conjecture for p equals 2? Is there a new conjecture that's more plausible? I'm just curious.
No, I don't have any idea. So no, and it doesn't seem like that the correction that we need is an algebraic one. You know that there is this algebraic corrections of coherence law distribution. Like if you have symmetric matrices, then you need some sort of algebraic correction by modifying the Cohen-Elstra distribution by taking into account the number of perfect symmetrical bilinear pairings or something like that. So here, there you can see that there is this clear algebraic correction, but here I don't think so. So it seems like more like some sort of geometric problem. This seems like a problem which has to do more with geometry than algebra. So I don't know.
Do you believe, I forget, do you believe that the co-kernel converges in distribution, or do you think it actually grows in N?
I think it still will be tight, so it might be okay. So that's one direction I try to explore. The other types of simpler random matrices with some additional geometric structure and what happens there. And yeah, in the recent papers, I've seen examples where we have this Cohen-Elstra distribution for a certain set of parameters, but in kind of when we at criticality, we see some other behavior. We see some strange things like these heavier than Cohen-Elstra tail of the co-kernel and so on, which also appears in this case. So yes, there is some hope that we can understand things like this. But again, we can only understand this in a much simpler setting, with a much simpler geometry.
I see. Are there any other questions? Right, well, thank you both again for this pair of very nice talks. Maybe Louisa, if you want to stop the stream,